All right, we'll go ahead and get started. So first we'll start with some housekeeping notes. So as usual, if you do have any questions, go ahead and put them in the chat and we will go through them at the end. We are recording the session, so we will share it afterwards along with the slides. And we are excited for our part 2 of this presentation from our guest speaker, Chris Mathis. Chris has spent the last 40 years focusing on how buildings and building products perform, from energy efficiency to long-term durability and sustainability. He has an undergraduate in physics from UNC Asheville and a Master of Science in Architecture Studies from MIT, where his work focused on the energy use of buildings. He's the author of over 30 papers on various building science topics. He is a 39-year member of ASHRAE and currently serves on SSPC 90.1, the Commercial Building Energy Standard, 90.2, the Residential Building Leadership Standard, and is the past chair of the Residential Building Committee. As president of Mathis Consulting Company, Chris and his team provide a variety of professional building science and strategic planning consulting services to both public and private sector clients. So with that, Chris, the floor is yours.
Thanks, Kelly, and thanks everyone for joining today. This is part 2 of a session called Why Buildings Matter, and we're going to focus today on ASHRAE 90.1. Just to recap from last month's presentation, we learned that buildings matter really more than we know. There's a bunch of pesky trends going on. We talked about some of the things that building professionals may have to address. As Kelly said, I'm a nerd, I'm old, I've been doing this for a while. I'm going to share some stuff today that hopefully will be useful to you. We learned last month that I'm a beekeeper, so there's a whole bunch of really cool building science in the honeybee. But key message here is if you like food, thank a honeybee. About 1 out of every 3 bites you eat, they're responsible for. We reviewed the nation's energy profile and showed that buildings were the dominant energy use sector. It's because of our incredible appetite for this stuff. We get this fuel to satisfy that appetite from a lot of sources, most of which are still fossil fuels, a finite resource. And if we project out to 2040, it looks like we're going to want more of everything. And if we look worldwide, everybody everywhere is going to want more of that same precious resource. This is all happening at a time when world population is growing. We're coming up here on, I see this graph is screwed up, but we're coming up on 8 billion people here in a year or so. We learned a bunch of stuff about water and the connection with drought conditions, water availability, power generation. It takes over half the water, extracted surface water, every day in the United States to make electricity, providing cooling for coal and nuclear plants. We looked at population migration and water availability and power availability, and we find that, you know, there's a discontinuity there that hasn't been addressed. We got a lot of commercial buildings in the United States. Most of them are old. Most of them were before 2003, 93%. That means that, you know, the 2004 edition of ASHRAE Standard 90.1, this thing that we're trying to be 40, 50, 60% better than, most of these buildings don't even meet that standard. If we look at residential buildings, roughly 1% new, roughly the same vintage issues. We've got this big gorilla called existing buildings, which we ignore. It's like this giant ship that we've talked about, this ship of energy, and it's a ship full of holes. They're old buildings, they're under insulated, they're bad air sealing, they've out-of-date HVAC and lighting systems. There's a whole bunch of opportunity there. We tend to spend our time focusing on the sexy stuff up on the deck of the ship. But my admonition and recommendation to everybody is, let's first plug the holes in the ship. The trouble with basic old energy efficiency is it's boring. Powerful, we learned last month, but very boring. So we've got to do a better job of conveying the power of energy efficiency, power to clean the air, the power to conserve water, the power to meet the needs of a growing population worldwide. We looked at some pesky trends. The biggest by far is climate change and the implications of climate change, and 9 of the 10 hottest years that we've ever recorded have been in the last decade. Well, what does that mean if we want to give air conditioning to everyone? So it's a big deal. It's a really big deal. We don't have enough of those precious finite resources to provide that much food to satisfy that energy appetite. Now, this is all happening at a time when we're expecting more of our buildings. We expect them to be safe. We expect them to be energy efficient. We expect them to have great durability and resilience. And in the US, we spend an average of 94% of our time indoors. And that building is likely going to be around for about 100 years. So historically, we've relied on the building code to handle these issues. I'm going to give you in the next 15 slides a kind of a quick history of the building code. First, what is the code? Okay, the code is the least safe, least strong, least energy efficient building allowed by law. In other words, we're not allowed to build it any crappier. Now, that doesn't mean that a code building is a crappy building. It means that the code building is the starting point for anything that we want to do different and better. Unfortunately, we generally wait on disaster to improve our codes. Now, the first code we know about was the Code of Hammurabi. It was found on some stone tablets. No, not those stone tablets, some other stone tablets. And there were all these rules on them, not the 10 big ones, but, you know, a bunch of rules. And about 26 of those rules that Hammurabi wrote governed construction. And it said things like this: if a builder builds a house for a man and the house falls down and kills the man, the builder's put to death. Now, that's kind of an Old Testament sort of code, wouldn't you say? The Emperor Nero didn't like the slums around Rome. He had to burn to the ground and had rules established to rebuild those buildings. How far away from the city, how far away from the city walls, where would the latrines go, how far away were the animals kept. The Great London Fire, we know about the Black Plague, but one of the things that happened following that fire was things like, oh, we have to be able to get our firefighting equipment to the building. Oh, we need to have fire breaks between buildings. Here in this country, the Great Chicago Fire, you know the story about Mrs. O'Leary's cow. She supposedly kicks over a kerosene lamp in a barn and burns down the city of Chicago. What you didn't learn was that fire bankrupted the insurance industry. The insurance industry said, we're out of here. Chicago says, hey, wait a minute, we got a city to rebuild. And the insurance industry said, if you want us to help you rebuild, you've got to let us help write the rules. And that's how we got some of our first and most important fire safety rules regarding things like fire stops in walls, the use of gypsum and fire rating of gypsum assemblies and things of that nature. 30 years later, the San Francisco earthquake, major influencer of the codes we have today governing high-risk areas where you've got a seismic activity. Now, we could say that the oil embargo of the early 70s, most of you probably weren't born then, but for those of you who were, in the early 70s, there was an oil embargo that kind of caused an energy disaster for the country and other countries. Our response was the nation's first energy code. It was called ASHRAE 1975, and that was actually what we now know as ASHRAE Standard 90.1. What did we do? Well, one of the things we did is we tried to save energy. And we did it a lot of different ways. We sold a bunch of insulation, and we developed consumer signals. We started giving consumers signals on energy performance that they didn't have. Your actual mileage may vary, but suddenly you had a means of comparing things. Now, somebody might say in the South that this is an energy efficient building, but those early codes, they were so focused on heating that if I did the math, this was a much more energy efficient building. That's because the windows we had at the time sucked. They were terrible. So what did the window industry do? Well, they innovated. They developed new technologies, low E coatings, gas fills, heating energy savings, and then eventually cooling energy savings, and so on and so forth. This particular storm, Hurricane Andrew, this disaster completely changed the building code in all coastal climates and high wind zones. This one storm was responsible. I call this is the storm where we learned that it's not okay to put a roof on a building. You actually have to attach the roof to the building. In this particular storm, 90% of the homes in Dade County, Florida were damaged because roofing materials blew off, hit the neighbor's windows, broke the windows, and then it rained. And it rained, and it bankrupted the insurance industry. And the insurance industry said, see you, Florida, we're out of here. And Florida says, wait, we've got to rebuild. And the insurance industry again said, you want us to help you rebuild, you got to let us help write the rules. And now in every high wind zone from Galveston, Texas to Long Island, we've got impact resistant glazing and greater anchoring systems on roof systems for high wind zones. One storm changed the building code. Some parts of our country are prone to seeing these kinds of storms regularly. Hurricane Katrina, largest storm we've seen in U.S. history. Following this storm, Louisiana and Mississippi had voluntary building codes. Following the storm, they adopted mandatory building codes. My home state of North Carolina, we had some tornadoes tear through. This was pretty interesting. This house was actually picked up and moved 8 feet back on its foundation. So in this particular disaster, this is one where we learned that it's not okay to put a house on a foundation. You actually have to attach the house to the foundation. And if you're going to build with lightweight building materials, do not be surprised when they become airborne. These 2 cars used to be in the garage. Now, Superstorm Sandy, that caught us all by surprise. First of all, this is one of those first named storms back in 2012. Why was this a superstorm? Well, I will tell you why. It hit a particularly vulnerable part of our country at high tide at prime time. So we all got to watch it on television. We got to see infrastructure being washed away and roads going away. We got to see the entirety of Manhattan essentially blacked out. The thing that's surprising to people is that Superstorm Sandy was a baby storm. It was a Category 1, 110 mile an hour gusts. Baby storm by comparison. We freaked out when the grid went down in New York and 8 million people were without power. When the grid went down in India, 350 million people were without power. What would we do if 350 million people were without power? Oh, wait a minute, that's all of us. Greensburg, Kansas. Devastation like you just can't imagine. Moore, Oklahoma, this particular storm just really ticked me off because we know this in something like 20 minutes, 12,000 homes were destroyed. The reason it ticks me off is that we know where these Category 5 tornadoes occur. They go through Moore, Oklahoma about every other year. We know where the Category 4s occur and the Category 3s and the Category 2. We know where these storms are. Same thing with the hurricanes. And what we do in Florida is, we plan for hurricanes because we know that storms like Irma and Harvey and all these others are going to come through. It's not just Florida. Here's the Carolinas and Georgia. And those pesky climate scientists kept telling us that we're going to have more frequent extreme events. This satellite photo shows 3 hurricanes active in the Caribbean and Atlantic Basin at the same time. We watched as Puerto Rico got hammered by Maria. Devastation. Doesn't matter how heavily you build when you have a storm that size. And moving water in a focused place can be very damaging. And it took months. It actually took over a year to restore power to the island. And really no state is immune to these events. This picture right here, this is probably a pretty important picture. This is a Category 5 storm. Actually, this is the largest storm in modern history since we've been tracking these things. This is Tropical Cyclone Haiyan. This was a Category 5. As a matter of fact, we don't have a Category 5, a category for this storm. You know, Superstorm Sandy had 100-mile-per-hour gusts. Tropical Cyclone Haiyan had 100-mile-an-hour sustained winds and gusts in excess of 260 miles per hour. And the devastation, like we can't imagine. And in Florida, we put these hurricane magnets in place and we put wings on them. I jokingly say this, but you know, this is somebody's castle. This is somebody's home where the grandkids come to see grandma and grandpa. And they come on vacation or they go see the mouse at Disney World. You know, this is somebody's castle. Unfortunately, within the code arena, we wait for disaster. We wait for disaster. Now, last month, we talked about the challenges of market transformation and what are the things that we need to do. Dan was asking me this earlier. What are the things that we could do to help advance the cause? Well, there are only two forces, push and pull forces, which we talked about. But the resistance in this system is our resistance to change. We, as a building industry and just about every other industry, resist change even when it's in our own best interest. So here we are, recent code history with regard to ASHRAE. We got 2016, we've got the IECC, we got 2019. We're working on 2022 right now. Some of the things that you know are going to be involved in that push and pull is what are we going to advocate for? Are we going to reduce building air leakage? Are we going to address thermal bridges? Is it going to cover every building type? Or are we going to build better envelopes? What about testing and commissioning? What about peak power? We talked about the timing of our energy demand. You know, we're expecting all this air conditioning at exactly the same time. And then what are people going to do? What kind of feedback and communication systems are we going to have in place so that they know how the buildings perform? ASHRAE Standard 90.1 is a code. It's a minimum standard. It is not the best building. It is the least energy efficient building allowed under this standard. There's a SI version, there's an IP version, and it serves as the national model for states to evaluate their code. Again, it defines the minimum, and it's one of these standards at ASHRAE that's on continuous maintenance, meaning if you see something that you think should be improved, you send that into the committee and they have to deal with it. We look at continuous maintenance proposals all the time. Current edition is 2019. Now, our goal in 2019 was to be 50% more efficient than 2004. Why is that important? Remember, 93% of our commercial stock was built before 2004. And we're trying to build buildings today that are 50% more efficient than 2004. So I just laid out a landscape of change. There were some big changes, some pretty big envelope changes back in 2007, 2010. The HVAC community doesn't often pay a lot of attention to those envelope changes, except that when we're doing a load calc, those are the inputs to our load calculation to size equipment. So I'm going to encourage everybody on this call to do this most boring thing and look at the minimum requirements by climate zone for the building envelope. Because there was this ad back in the 70s that says you never get a second chance to make a first impression. Well, that building envelope is the first impression that's going to be with that building typically for its life, probably 100+ years. This shows how the code has improved over year. If we index it to that first code back in 1975, you can see how the code has gotten better and better. And then long about 1999, we put it on this 3-year cycle of continuous maintenance. And our target has been to continually do better. Key here is that doing better in the code minimum, is still a long way from net zero. Let's look at a couple of examples. This is steel wall insulation requirements. U factor, the kind of the, think of it as the inverse of the R value. You'll see that for long periods of time, there were no improvements to the insulation values. And really the insulation values only started improving in middle America, climate zones 2, 3, 4, and 5, starting in 2013. Said another way, here's steel wall U factors from 2010, 13, 16, and 19. Currently, we've been doing this. So for 4 code cycles, roughly 12 years of work, we've made no improvements in wall performance, in minimum wall performance. Resistance to change. There are some pretty cool new things in 2019. And I want to just talk a little bit about some of these because we have a limited amount of time today. But, we talk about commissioning in the HVAC community as bringing the system online and testing to make sure that every piece of equipment and all the ductwork and all the piping and all the pumps and all the coolant, all of those things work properly. But that's just like saying, I need my blood system and my heart and my arteries and my veins to function properly. Well, I also have lungs, and I have an electrical system in the form of my brain, and I've got my skin that I've got to protect. So this notion of commissioning is now expanding to all areas of the standard, where if somebody's installing lighting controls, we want those lighting controls to be properly commissioned so that to achieve the levels of efficiency implied by the standard, you have to make sure that you're delivering that. Same thing with air leakage. If you're installing an air barrier, having it commissioned or tested, probably a really good idea because you're basing your envelope air sealing assumptions in your load calcs on how that air barrier is performing. So this notion of commissioning is going to be extending beyond HVAC. With regard to the building envelope, we used to talk about how wood windows perform and how vinyl windows perform, how aluminum windows perform. And what we realize is that A, most windows these days are composites. And B, why should we have different performance requirements based on material? Isn't it about performance? Let's base it on performance. So where you used to see aluminum and or metal and non-metal, now you have material neutrality. You just have fixed windows and operable windows. That's a big deal. And remember, they're not the best windows you can install. They are the worst windows you can install. We've made some slight improvements in air leakage reduction. For my HVAC colleagues who were doing load calcs, envelope air leakage is probably one of the single biggest contributors to your error bars in your load calculations. What if I tested the building and told you its air leakage characteristics? Wow, you do a better job sizing equipment and designing controls and delivering the precious heating and cooling that's needed. Sadly, cost-effective levels of air leakage, even though we know that it's cost-effective, there are, it's a consensus process. You have to get enough votes, and we're unable to achieve the votes so far to get the levels of air leakage reduction that we know are cost effective. Again, commissioning the envelope. Oh, did you install the insulation? Yep. Did you install the insulation properly? What do you mean properly? I'm one of 50 people that's written a book on insulation. They all say the same thing. People ask me, Chris, what's your favorite insulation? I say, it's the one that's installed properly. If you haven't gotten to know a lighting designer recently, get to know one and thank them. Not just for really cool LEDs that are now dimmable in every color under the rainbow, but for the advances in lighting controls. I suggest that there's probably as much or more lighting power savings embodied in the controls of advanced lighting systems as there is in just new light bulb and fixture technologies. One of the things that the lighting folk have done is they've recognized something that we're trying to do in envelope and mechanical as well, and that's to have simplified compliance technique. Oh, wait a minute, most buildings are short and fat. 85% of the commercial buildings in America are less than 25,000 square feet. They're short and fat. They're not the big, iconic all glass high rises. They're the local dentist office or office building or office park or school or church. I mean, they're short, fat buildings. Simple. What is a mechanism to deliver compliance for those simple buildings? Okay, let's see, where am I? Mechanical. Data centers are a big deal. Your part of the world, data centers are a big deal. There's a new standard, 90.4. So once you get over 10 kW, there's a whole separate standard for you in outside of 90.1. Lots of improvements in pump efficiencies and equipment efficiencies, those that are covered under the federal mandates, as well as those that are not. A change in fan energy index versus fan efficiency grade, because there's been a lot of improvements in fan power and fan motor ratings. How to do energy recovery. When do you use economizers? What is an economizer? What makes an economizer work properly? Those are some things that have been improved on the mechanical side. For those of you who do building modeling, like we do in our shop a lot, that falls under this energy cost budget aspect of 90.1. It's like, what's the proper way of modeling, doing building thermal model to show compliance with 90.1? Now, that's not a trivial question. And as you know about computer programs, the old garbage in, garbage out, it's really easy to screw up on the garbage inside. And what we used to do is we just throw more horsepower at it. We'd throw more BTUs at it. We'd throw greater size at it. We'd have more tons at it. And we now understand and realize unequivocally that that is a non-sustainable solution with a whole bunch of other problems associated with it. There are some new modeling rules regarding what's plugged in. How do you quantify what's plugged in? What are those controls? How do you control those receptacles where things that can and cannot be turned off exist? This is just a tease, because what we're doing in the 2022 edition of the standard is what we're working on right now is 2022. This is stuff that's in 2019. Why is this important? I'm sure that many of you have participated in projects that talk about, we'd like to get to net zero. We don't like to have a conversation about net zero and say, what's the minimum code? No. Again, the code is the starting point for doing better than. We owe the green building community a debt of gratitude. We owe them our thanks, if for no other reason, they have given us the language of better than. meet the code? Are you doing 15% better than, 20%, 30%, 40% better than? We're now used to having that conversation. I want to do better than that minimum. And net zero being one of those areas where we'd like to be really better than. Well, so what does net zero look like? Well, here's that same graph of improvements in the standard. And, you know, Architecture 2030 is a pretty aggressive glide path. I will guarantee you that standard 90.1 is not going to get to net zero or really even provide a framework for net zero by 2030. Our glide path, you know, we're looking under every leaf and rock and dustbin that we can find to find every little kilowatt and BTU that we can find that's cost effective. Because one of the big tests within 90.1 is cost effectiveness test. So at our current rate, we might get to a kind of a net zero framework by 2050. This is just Chris speaking. Okay, this is just strictly opinion. I go back to my ship of energy. Remember, we'd like to think that if I put enough PV up in the desert and enough wind power in Texas and Iowa, that I'm going to be in great shape. I've got enough power. Let's not confuse renewable energy with energy efficiency. Just because I have lots and lots of good renewable energy doesn't mean that I should be wasteful with it. So don't add EE and RE together. They have different life cycles, they have different implications, and they certainly have different time implications. In the old code, we had these climate zones. Now, this is an example of the government trying to help us. This is the government telling us that climate occurs along county boundaries. Okay, we know that's not true. And in a place like Arizona, where a lot of you are right now, you have 10 counties, 10 big counties. A lot of your counties are bigger than some of our states, okay? By contrast, over here on the right-hand side, my home state of North Carolina has 100 counties. I know we're crazy, but climate doesn't occur along county boundaries, but we use climate maps like this to establish code criteria. Well, ASHRAE has a standard, Standard 169, which updates these maps. And in the latest version of the standard, you'll see very different map. And one of the things you find out about this map, let's just go back and look at North Carolina, for example. Here's climate zone 3, 4, and 5 in North Carolina. I live in that green part there up in the mountains in climate zone 5. Same climate zone as Chicago, okay? But North Carolina's got climate zone 3, 4, and 5. Here's how look how that map now changed. North Carolina has got a whole bunch of 3, a little bit of 4, and a little bit of 5. Well, if you looked at this map as a whole, you would see that almost all of those lines have taken a step northward. As we saw last month in the climate presentation, things are getting warmer, and those pesky climate scientists told us that the extremes are going to get more extreme, and that's exactly what's happening. Now, just because we have a new standard doesn't mean that everybody across the country adopts that standard. As a matter of fact, what happens is that ASHRAE develops a standard, DOE does this analysis on whether or not it's an improvement in efficiency. And if they announce it's an improvement in efficiency, they then toss it over the sound screen to the states. And then the states have to decide what they're going to do. And states do things at very, very different rates. And it's not unusual for there to be a 9, 12, 15-year lag between adopting cost-effective energy, minimum energy performance standard in a state. Just because we published and did the economics for 2019 and everything in 2019 was cost justified, it might be 2029, 2032, 2035 before that standard is adopted in the majority of states. Let's look at Arizona and California, some folk who are probably on this call. California's pretty aggressive with their energy code because they've got every climate zone in California. And so their Title 24 has been kind of the bellwether standard for some time. Arizona, not so much. As a matter of fact, Arizona is really one of those white states. I don't know if it has a statewide code. Maricopa County may have one, Pima County may have one. I don't know. The point here is the 2019 version of ASHRAE 90.1 is cost justified. Now, I could make also a pretty good legal argument that 2019 represents the standard of care, regardless of whether it is adopted by a state. People might argue with me about that, but if you are practicing architect or engineer and you're trying to decide what to do with a new building, wouldn't you want it to meet the most recent standard? And this problem of state code adoption is not just a commercial problem, it's also a residential problem. And there's sadly, a lot of delay in adopting the latest residential energy code. So what I might say to my architect friends on this call is, when you look at those tables in the ASHRAE Standard and compare to what you're currently specifying and installing, doing an all-glass building in the desert? How about wall insulation to reduce cooling loads? What are you doing to test your building for its air leakage characteristics before you go commissioning an HVAC system? To my engineer colleagues, if I'm that architect, I might say, I need to let my engineer know that I'm following this new standard so that when they do their load calcs. Now, this stuff's already been around for a while. And I think we saw that Arizona, as an example, is more than a decade behind. Now, if I'm an engineer, what does 90.1 1999 or 2019 mean for load calcs, equipment sizing, and selection? If I'm using the latest and greatest in the federal minimums and more efficient motors and more efficient pumps, what does my architect know about this stuff? Do they know that I'm going to be paying attention to their glass decision maybe more than I was before? We could go into all of this in painful and exquisite detail. It would be an 8-hour workshop, not a 1-hour presentation. Somebody has to take these kits of parts and put them all together. One of my favorite pictures to show is the Taos Pueblo, the oldest continually inhabited building in the US, I believe. 3 building materials: local mud, local grasses, local wood. 3 building materials, 1,100 years. How many building materials do we deliver to a typical job site today? Certainly not 3, not 30, maybe not even 300, maybe 3,000. And most of them are really not designed to work well together. And we toss this stuff over the sound screen to the general contractor and say, put it all together and make it withstand the forces of sun and wind and rain and sleet and 3-year-olds for 100 years. Do these new standards and the concept of delivered performance change what that general contractor should be doing? Should we be having these conversations between the architects and the engineers and the general contractors at the start of a project so that everybody will be working from the same baseline assumptions? We're going to do X% better than the code. We're going to do X% better than ASHRAE Standard 90.1 2019. Couple of other examples of some of this change. Let me see where I am time-wise. Running out of it. Let's insulate a commercial roof. One of my first jobs out of graduate school was to go to Phoenix, Tempe actually, and instrument a commercial building and measure the heat flux and temperatures and a bunch of other things about the building. And this was when I first learned that you could make ice in the desert. It's like I was checking these thermocouples and I'm going, this thing says it's like, 29 degrees last night, but the air temperature only got down to 45. How in the world did this get down to 29 degrees? And I learned about the power of night sky cooling and the work of Harold Hay back at Arizona State. But here's roof insulation requirements. And back in 1989, the R value for commercial roofs was set at about 15. That's that red bar across the top there, R15. And then we didn't do anything with that requirement for 20 years. And in 2007, we did the ASHRAE nerd thing. We did the life cycle assessment and found out that, oh, wait a minute, for most of America, R20 was cost effective. And when we updated our economics for 2013, we found that R30 was cost effective. Now, when we went from R15 to R30, you would have thought we were torturing children. Oh my goodness, the world is going to come to an end. Well, let's build a roof together. What's R15? 2 layers of 1 inch of polyiso insulation, 2 layers of 1 inch. What's R30? 2 layers of 2 inch. 400 years. Same thing on walls. With windows, going from the most common window in the desert Southwest, aluminum single glazing, to code minimum today, we're talking about 1/3 the heat transfer of U factor, yet we go to the desert and we build these all glass icons. Think about what we build. Let's compare a window to a wall. Okay, these are the values for climate zones 5, 6, and 7. You think of this as Chicago, Minneapolis, and Duluth, a long way from where you are. But look, we allow 7 times the heat transfer through the windows as we do the wall. What's wrong with that picture? Think about that. If I'm focused on heating, why would I put in a window this bad? If I'm focused on cooling, everything's about solar heat gain. Single glazed aluminum window has a solar heat gain coefficient of about 0.9. That means about 90% of the energy that hits that window comes inside and becomes air conditioning load. Well, the window industry didn't sit on their hands. They did a bunch of innovating and they realized that air conditioning energy is very expensive. So what did? They innovated and they developed glass that today is optically clear and blocks 70% of the solar gain. What are we installing in the desert? What are we installing in Southern California? What are we installing in most of America that wants air conditioning at exactly the same time? Oh, and that air conditioning load is driven by not the walls, it's driven by the windows. I will provide everybody a copy of these slides. Don't worry about trying to capture this stuff. I went to New York back before COVID, and I'm going, wow, does a building have to be all glass to be iconic? You've got the Chrysler building over there to the right, and the all glass new building there to the left. Building another all glass icon for my hotel room. I was giving a presentation in this all glass building, which was reflecting back another all glass. But we have a love affair with glass. We're not going to change that. But if we're going to use glass, we should be using dramatically different glass than what we have been. This is Jacksonville, Florida. This is one of my favorite photos. This is a giant heat exchanger. I mean, this is a giant multi-story apartment building with those concrete balconies cast solid all the way in through this. So what happens when the sun hits those concrete balconies? Think that changes the air conditioning load? We know how to hang balconies, but we didn't do it in this building. And so many of our buildings have all of these different systems going together, you know, the balconies, the windows, the all glass curtain walls, the aluminum, the steel, the parts that are well insulated, parts that are not well insulated. And we expect the performance of that building to be predictable and reliable. We expect it to be durable. We expect it to be sustainable and energy efficient. We expect it now to protect us from airborne pathogens. And we expect to be comfortable in it. Sometimes the messages are pretty simple. What is the code? The code is the starting point. The code is not leading edge. It's not superior. It's not exemplary. It's not even green. It's the starting point for all those things. If you go out to the Energy Star website or the LEED website and you look at the rating systems, it'll say, meet the code and do X% better, Y% better, Z% better. If you look at all these other different programs, these beyond code programs out there and utility programs, they all say, do better than the code. Well, the current minimum code is ASHRAE Standard 90.1. Do better than the code. We talked about the fact that a lot of people want to get to net zero. So here I am at building to the minimum. I know that I'm still a long way from net zero. But as I improve the code and improve the code, and we're constantly working to improve the code, the question is, okay, now when the minimum code moves here in 2 years, what are we going to do after that? What are the next steps? How far can we get to net zero? How far can we get to green? Where is the code in the landscape of green? There's way more to green than the energy performance of the buildings. But as we learned last month, the energy performance of buildings is our nation's single largest energy demand. And so if we truly want to be green, we have to do better than minimum code buildings. Now, it's not easy being green. We've made a bunch of mistakes along the way. In the early days of LEED, a bunch of really smart nerds got together and measured a bunch of LEED buildings, and they found that about 30% of them used more energy than allowed by code. Well, now, wait a minute, Chris, you told me that green buildings were supposed to be 20, 30, 40% better than. And this is where, you know, this is what I'm going to call growing pains, the early days of green. These growing pains showed that we got so busy chasing points that we forgot to deliver performance. And fortunately, LEED and all those other programs have really made a huge shift toward delivered performance, commissioning systems, measuring stuff, testing air leakage, commissioning air barriers, commissioning HVAC systems, commissioning lighting and lighting control systems, so that we're getting what we expected to get. As I said, there are a lot of objectives beyond energy performance. We've all been living through 2 years of COVID chaos. We expect our buildings to be safe. We want them to be safe. Indoor environmental quality is becoming a bigger and bigger issue. Thermal comfort the ability to use all the space in my building because it's comfortable space. It's becoming a bigger deal. If I'm building in the desert Southwest, I have to address water. If I'm building in Atlanta, Georgia today, I have to address the water demands of that building. What am I going to do to reduce its water demand? Maybe in Minnesota, in the land of 10,000 lakes, water is not as high on the priority list on somebody's green checklist, but I guarantee you it's on it. And if you're a greenie weenie like me and you're thinking about these buildings in terms of their global warming potential and carbon equivalence perspective, you might do all of this math in units of CO2e, not units of BTUs or kilowatts or dollars, but in units of atmospheric carbon. So what do? As building professionals, we've got a pretty serious challenge to get the latest tools in the hands of decision makers. For those of you who have not been involved in your local utility commission work or your local building code work or your local energy code work in your town, your municipality, your county, or your state, it's time to get involved, because what is needed is informed professionals to help those political leaders and policymakers make more informed decisions. Get involved. If your local school board is getting ready to do a bond referendum on building the next school, for goodness sake, get involved in helping to make sure that that school is way better than minimum code. When you go to an ASHRAE meeting or an AIA meeting or a USGBC meeting, take a friend of a different profession. Bring an architect with you, engineers. Bring your local building officials to your meeting. Buy them the rubber chicken lunch if you have to. Get everybody on the same page. Commission stuff and measure stuff. When we commission envelopes and HVAC lighting systems controls, when we commission those things so that they actually perform, we almost always exceed our efficiency expectations just because things are working well together. Never get a second chance to make that first impression. And when you're doing existing buildings, now existing buildings are hard. They require the best of us. They require the best of our engineering, the best of our architecture. They're harder. Measure stuff. Get in there. Don't go modeling an existing building and making a bunch of assumptions about it. Just get in there and measure stuff. Measure the leakage, measure the comfort, measure the airflow, and then you can do a better job of prioritizing what you need to do to bring that building up to at least minimum code. Don't forget existing buildings. Charles Darwin said it's not the strongest of the species that survives, nor the most intelligent, but the one most responsive to change. We have got to be agents of change. We have to be leaders of change. We have to be responsive to change, like climate change, like COVID, like airborne pathogens, like peak power depletion, like fossil fuel dependence. We have got to be responsive to change and to be leaders to the change that we need in our industry. Once again, I'll end with the future's in your hands. And thank you very much for your time today. And I hope we have a little bit of time for Q&A. And I'll turn it back over to Kelly.
All right, thank you, Chris. So as of right now, we actually don't have any questions. So if you guys do have questions, go ahead and type them in the chat. There was one comment from David Anderson. He said that cities and counties have adopted newer versions than the state. So I know you had mentioned you weren't sure about the cities and the counties in Arizona. So, and any questions? You can also come off mute if you'd like to ask questions.
Chris, Dan Honey calling. One of the challenges I think we're experiencing in Phoenix that I understand has adopted the IECC 2018 code is that many building inspectors don't have the education, the understanding, and the awareness what to look for to make sure that the buildings are being built in conformance and compliance to the standard. Have you been challenged with that? With what capacity?
Yeah, that's a great one, Dan. I have had the incredible good fortune to do classes for over 2,000 building inspectors and do classes on specific editions of the code and what they need to look for. Now, we treat our building inspectors like second-class citizens. We need to engage them on the front end. Their kids go to the same schools as your kids. They go to the same church. They buy groceries and gas at the same stores. I mean, we've got to do a better job of interacting. I hear what you're saying, and I say that is an untapped education opportunity. When I get an opportunity to talk to building officials, I leap at it because they want us to succeed. They're not there just as the code police. They actually want us to succeed. When I ask architects and engineers to engage their building officials and invite them to the first project meeting, they look at me like I have three heads. And I say, now, wait a minute. Don't you want your building official to know that you're trying to be 30% better than code? That building official is going to be a contributor to your project when they show up on site and go, hey guys, one of your code objectives is at risk over here because X is not connected to Y. We need them. We need them to be better at understanding this. So I see the building official community develop those CEU programs specifically targeting building officials like I did. And in our state, our building officials have to have 36 hours of continuing education every year. And until 2011, they had gotten no training on the requirements of the energy code. And we did this training in North and South Carolina, and it was transformational because guess what? At the end of the day, those building officials go home to their home where they're using energy and needing to be comfortable and have their family protected for 100 years. So engaging the professionals in the building inspection and in the building department would be a huge untapped opportunity, if you haven't already done that, to build and strengthen valuable relationships.
Thank you, Chris.
All right, and there are no other questions. Everybody is just saying thank you for the presentation. So I will echo that. Chris, thank you so much for this presentation and for last month's, for both parts. They were excellent, so thank you.
Well, thank you for having me, and I'll send a copy of the presentation to you when I get a chance here.
All right, and then I will share it with
everyone.
everybody on the call, and thank you, everyone.
Thank you.
Chris, thanks again.
Thanks very much.